The world moves at the speed of light. Every email you send. Every video you stream. Every financial transaction that crosses the globe. It is all part of a colossal, non-stop flow of data. A torrent of information moving invisibly around us. We take this speed for granted. We expect instant connection. But the foundation of our digital world isn't built on satellites or radio waves. It's built on something far more fundamental. It is built on glass. Hyper-pure, hair-thin strands of glass. And it's built on light. Beams of focused light, trapped inside the glass. This is the story of the invisible highway. The blueprint for a technology that seemed impossible. A technology that required engineers to challenge the laws of physics. To invent new materials that had never existed before. And to make a $1 trillion bet that they could tame light itself. This is how fiber optics really built your digital world. Act 1, the impossible dream. Our story begins in the mid-20th century. The world was connected by copper. Thick, heavy cables crisscrossed continents and oceans. They carried our voices. They carried our telex messages. They carried the first, slow trickles of digital data. But copper had a fundamental limit. It was a bottleneck. Electrical signals degrade over distance. They are vulnerable to interference. Pushing more information required more power. Thicker cables. More and more complex amplifiers every few kilometers. Engineers were hitting a wall. The demand for communication was exploding. But the physical medium itself was holding progress back. The world needed a new highway for information. A medium with vastly more capacity. In 1966, a young engineer in England had a revolutionary idea. His name was Charles Cow. Working at Standard Telecommunication Laboratories, Cow looked at the problem differently. He didn't see it as an electrical engineering problem. He saw it as a physics problem. Scientists had known for centuries that light could be guided. The phenomenon was called total internal reflection. Light traveling through a dense medium, like water or glass, strikes the boundary with a less dense medium, like air. If it hits that boundary at a shallow enough angle, it doesn't escape. It reflects back inside, perfectly. It becomes trapped. Cow's idea was radical in its simplicity. What if we could use this principle to send information? What if we could replace electrical pulses in copper with light pulses in a glass fiber? Light has an incredibly high frequency. In theory, it could carry thousands of times more information than the best copper wires. It would be immune to electromagnetic interference. It was a breathtaking vision. But to most, it was pure science fiction. There was one, seemingly insurmountable problem. Glass wasn't perfectly transparent. Even the clearest glass in the world absorbed light. In 1966, light sent down the best available glass fiber would die out completely in just a few meters. The signal loss was astronomical. To send a signal across a city, let alone an ocean, was a fantasy. The scientific community was deeply skeptical. But Charles Cow was not just a dreamer. He was a methodical physicist. He studied the problem intensely. He determined that the signal loss wasn't caused by the glass itself. It was caused by impurities within the glass. Microscopic flecks of metal and other contaminants. Cow did the calculations. He published a landmark paper. In it, he declared that a glass fiber could work for long-distance communication. But it would require a material of impossible purity. It needed a signal loss, or attenuation, of no more than 20 decibels per kilometer. This meant that after 1 kilometer, 1% of the original light would still remain. At the time, the best optical fibers had a loss of 1,000 decibels per kilometer. The challenge was clear. Cow had drawn a line in the sand. He had defined the goal. Now, someone had to invent a material that did not exist on Earth. Someone had to create a glass so pure, it was fundamentally different from any glass ever made. The race to forge the invisible highway had begun. Act 2, Forging the Glass, Taming the Light. The challenge laid down by Charles Cow echoed through research labs around the world. Most consider the 20 decibels/km goal to be a fool's errand. But not at a company in upstate New York. Corning Glass Works. Corning was a company built on mastering glass. From heat-resistant Pyrex to the television cathode ray tubes in every American living room. Their expertise was legendary. In 1970, a small team of physicists took on Cow's challenge. Robert Maurer, Donald Keck, Peter Schultz. They weren't trying to purify existing glass. That method had failed. They started from scratch. Their approach was different. It was called chemical vapor deposition. The idea was to build the glass molecule by molecule. They started with incredibly pure chemical vapors, like silicon tetrachloride. These gases were heated inside a fused silica tube. As the tube rotated in a high-temperature lathe, the chemicals reacted with oxygen. They formed a fine, ultra-pure glass powder, or soot. This soot deposited itself on the inside wall of the tube. Layer by excruciatingly thin layer. The team could precisely control the process. To create the core of the fiber, they added another gas, a dopant like titanium or germanium. This slightly changed the refractive index of the glass. It made it optically denser. After building up dozens of layers, the tube was collapsed under intense heat. It formed a solid glass rod, called a preform. This preform was a perfect macroscopic model of the final fiber. It had a hyper-pure core. And it had a surrounding layer of pure silica, the cladding. This difference in optical density between core and cladding is what would trap the light. Now came the final, delicate step. The preform was placed in a tall drawing tower. Its tip was heated in a furnace to over 2000 degrees Celsius. A molten bead of glass fell from the tip. Gravity pulled it down, stretching it into a hair-thin strand. A strand of the purest glass ever conceived by man. One day in August 1970, Donald Keck was testing their latest sample. He injected light from a laser into one end of the new fiber. He walked to the other end, hundreds of meters away, to take a measurement. He looked at his detector. He saw a tiny point of light. It was much brighter than he expected. He thought his equipment was broken. He ran his tests again. The numbers were unbelievable. He scribbled in his notebook, 17 decibels/km. They had done it. They hadn't just met Cow's challenge. They had shattered it. It was the shot heard round the world in the telecommunications industry. The impossible was now possible. But the perfect medium was only half the equation. You still needed to get information into the fiber. And you needed to get it out again. This required a whole new ecosystem of technology. The light source had to be microscopic. It had to be powerful and efficient. And it had to be switchable, on and off, billions of times per second. The solution came from the burgeoning field of semiconductors. Engineers at Bell Labs and elsewhere perfected the semiconductor laser. A tiny chip that could convert an electrical signal into a precise, intense beam of light. At the other end, they needed an equally fast receiver. This came in the form of photodetectors. Semiconductors that could instantly convert an incoming light pulse back into an electrical signal. By the late 1970s and early 1980s, the first complete systems were being built. Companies like AT&T, MCI and Northern Telecom ran experimental trials. They connected telephone exchanges in cities like Chicago and Atlanta. The results were astonishing. A single pair of fibers could carry thousands of phone calls simultaneously. More than a giant copper cable. The era of copper was officially ending. The blueprint for light-based communication was complete. Now it was time to build the revolution. Act 3, the revolution unleashed. The 1980s saw a massive, high-stakes gamble. Armed with Corning's fiber and Bell Labs lasers, telecommunication companies began a colossal infrastructure project. It was a land rush. Companies like MCI and Sprint raced to build their own national networks. They bought right-of-way along railway lines. They used special plows that dug trenches, laid the fiber optic cable, and buried it in a single motion. AT&T began aggressively replacing the copper in its own long-distance network. Billions of dollars were invested. It was a bet on the future. A bet that the world's hunger for data would only grow. But a new bottleneck emerged. Even with hyper-pure glass, light signals still faded over very long distances. Across a continent, or an ocean, the signal needed to be boosted. The early solution was clumsy. It was called a repeater, or a regenerator. Every 40 to 50 kilometers, the cable ran into a complex box of electronics. Inside, the faint light signal was detected. It was converted back into an electrical signal. The signal was cleaned up, amplified, and then used to power a new laser, which shot a fresh, strong light pulse down the next length of fiber. This optical to optical conversion was slow. It was expensive. And each repeater could only handle a single stream of data. It was a major roadblock to unlocking the true potential of fiber. The breakthrough came in 1987. An engineer named David Payne at the University of Southampton was experimenting with exotic fibers. He created a fiber doped not with germanium, but with the rare earth element erbium. He discovered something incredible. If you took this special fiber and pumped it with light from a simple laser at a specific wavelength, it would glow. The erbium atoms would become excited. If a weak data signal entered this glowing fiber, it stimulated the erbium atoms to release their energy. That released energy perfectly matched the incoming data signal. The result? The data signal was massively amplified. And it never left the optical domain. It was an all-optical amplifier. The erbium-doped fiber amplifier, or EDFA, was born. It was elegant, simple, and staggeringly effective. One small EDFA could replace an entire rack of complex electronic repeaters. It was the magic ingredient that made transoceanic fiber optic cables truly practical. But the final piece of the blueprint was yet to come. The piece that would unleash the internet. Engineers knew that light came in different colors, or wavelengths. What if you could send multiple data streams down a single fiber, each on its own unique color of light? Like having hundreds of separate lanes on the same invisible highway. This concept was called wavelength division multiplexing, or WDM. With the invention of the EDFA, which could amplify all colors of light at once, WDM became a reality. Engineers developed filters and prisms that could merge dozens, then hundreds of different colored signals onto one fiber. And separate them perfectly at the other end. The capacity of the existing fiber networks exploded. It didn't double or triple. It multiplied by a factor of 1,000. It was this combination, the pure fiber, the optical amplifier, and wavelength multiplexing, that created the world we know today. It created the backbone for the World Wide Web. It enabled the rise of search engines and social media. It made high-definition video streaming possible. It allowed global financial markets to operate in microseconds. Every part of our connected society is built upon this foundation. A foundation of pure glass and controlled light. The vision of a lone engineer. The painstaking work of material scientists. The genius of optical physicists. It is the triumph of a blueprint that turned science fiction into the invisible infrastructure of our entire civilization. The light in that fiber carries more than just data. It carries the sum of human knowledge, creativity, and commerce. A silent, invisible highway, flowing beneath our feet, forever changing the world.